Hi, did you know that matter that makes up you, me, planets, galaxies, and possibly most other stuff that we can see forms only about 15% of all the matter in the universe? The remaining 85% is actually dark matter, which, together with the ordinary matter, forms around 27% of all the content in the universe. In this episode, we will explore the observational evidence supporting the presence of this elusive dark matter around us. Let's begin. The term dark matter was first coined in the 1930s by the Swiss astronomer Fritz Zwicky. While studying the Coma cluster of galaxies, which contains more than 1,000 galaxies, Zwicky realized that the galaxies emitted far less light than expected for the total mass of the cluster. This mass was calculated using the virial theorem, which we have discussed in an earlier video, a link to which is provided in the description below. Basically, the virial theorem provides a relation between the average velocity with which the galaxies are moving in the cluster and its total mass. By measuring this velocity, Zwicky calculated the total mass of the cluster, which was underestimated by almost 3 orders of magnitude relative to the mass expected from the luminosity of the stars alone. This led him to conclude that the mass of the cluster was too small to prevent its galaxies from escaping the gravitational pull of the cluster. Consequently, Zwicky suggested that there was something else which acted like a glue to hold the cluster of galaxies together. He named this glue dark matter. Dark because it was invisible, and matter because it had gravitational effect on the surrounding stuff just like ordinary matter does. But it wasn't until the 1970s that the American astronomer Vera Rubin confirmed the existence of dark matter by studying how individual galaxies rotate. Vera Rubin and her colleagues found that individual galaxies may contain invisible mass which may be attributed to dark matter. Rubin studied the rotational curve of galaxies. A rotation curve is a graph showing the orbital speed of stars or gas in the galaxy as a function of their distance from the galaxy's center. Kepler's third law states that the square of the orbital period of a planet around the Sun is proportional to the cube of the orbit's semi-major axis. So this law basically implies that the orbital velocity of objects rotating around a massive body should decrease as the distance between the object and the center of mass increases. For instance, here on Earth, our planet's gravity keeps us from flying away, and the Sun's gravity keeps our planet orbiting on an annual schedule. Since Sun is the most massive object in the solar system, its gravity makes the planets, asteroids, and comets orbit around it. Objects that are further away from the Sun orbit more slowly because they feel less of a pull from the gravity of our central star. Our galaxy has about 100 billion stars, and our Sun is only one of them. The galaxy also has a lot of gas and dust where stars originate. All of these things rotate around the center of the galaxy. If there weren't anything else in the galaxy besides stars, planets, gas, and dust, the stars farthest from the center would rotate more slowly than the ones closer to the center. But observations show that this is not true. Stars farther away actually rotate faster. The only way scientists can explain this is if there is a lot of matter which is invisible to the eye, aka the dark matter. In fact, the flat rotation curve implies that the total mass of a galaxy can be given by this relation, where r is the distance from the center of the galaxy corresponding to the flat part. The exact value of r is actually not even important, as long as the velocity as a function of r remains constant. This means that the dynamical mass of a galaxy when compared with the visible mass comprising stars and gas reveals the presence of dark matter in spiral galaxies. Another strong observational evidence in favor of dark matter comes from its indirect observations. That's right. Since astronomers cannot see dark matter directly, they have devised alternate ways to investigate it. It's like looking at a shadow and making a guess about what is casting this shadow. These observations are made using a technique called gravitational lensing. When light from distant stars pass through a galaxy or a massive cluster of galaxies, the gravity of the matter present therein causes the light to bend. As a result, the light looks like it is coming from somewhere else rather than from its actual origin. The amount of bending helps scientists learn about the dark matter which is there by comparing the total mass of the system to the mass implied from stars and gas emitting electromagnetic radiation. Essentially, this boils down to the fact that even though astronomers cannot see dark matter, they can detect its influence by observing how its gravity bends and distorts light from more distant objects. By looking at the area around massive galaxy clusters which contain both normal and dark matter, astronomers can identify warped background galaxies gravitationally lensed by the cluster and reverse engineer their distortions. Sophisticated mathematical models of these results shed light on the location and properties of the densest concentrations of matter in the cluster, both visible and invisible. The twofold advantage of gravitational lensing is that it not only allows for modeling the concentration of mass of the foreground concentration, but also allows astronomers to learn about the farthest galaxies in the universe whose light would otherwise may not have reached us. The universe appears to have about 5 times more dark matter than regular matter, and its structure may center on an immense network of dark matter filaments that stretch between galaxies and grow over time. Areas where concentration of these filaments intersect also hold massive visible structures like galaxy clusters, further suggesting that the distribution of ordinary matter follows the dark matter. In fact, most simulations whose videos or images you see, including this one, simulate dark matter and then later add on luminous mass on top of it such that its various properties match with the observables of galaxies such as their color, sizes, and stellar mass. State-of-the-art technology is now being employed to explore lensing by individual galaxies in smaller mass concentrations such as galaxy groups to explore mass distribution and galaxies at high redshift. NASA's Nancy Grace Roman telescope, formerly known as WFIRST, is an infrared telescope similar to Hubble but with 30 years of technological advancements integrated into it. It will map the infrared sky with the same depth and resolution as Hubble while observing 100 times more area on the sky. Roman is scheduled to be launched in 2027. It will build on previous dark matter studies by using the so-called weak gravitational lensing that tracks how smaller clumps of dark matter warp the apparent shapes of more distant galaxies. Observing lensing effects on this more refined scale will enable scientists to fill in more of the gaps in our understanding of the dark matter. This mission will measure the locations and quantities of both normal matter and dark matter in hundreds of millions of galaxies. Throughout cosmic history, dark matter has driven how stars and galaxies formed and evolved. If dark matter consists of heavy sluggish particles, it would clump together readily, and Roman should see galaxy formation early on in cosmic history. However, if dark matter is made up of lighter, faster moving particles, it should take longer to settle into clumps and for large-scale structure to develop. Roman's gravitational lensing studies will therefore allow us to peer back in time to trace how galaxies and galaxy clusters formed under the influence of dark matter. If astronomers can narrow down the candidates for dark matter particles, we will be one step closer to finally detecting them directly in experiments conducted here on Earth. Most scientists think that dark matter is likely made up of an entirely new elementary particle that would fall outside the standard model that all currently known particles fit into. The standard model of particle physics is the theory describing 3 of the 4 known fundamental forces in the universe and classifies all known elementary particles. It is believed that the dark matter particle would interact only weakly with other known particles, making it very difficult to detect. Two leading candidate particles are postulated by theorists to describe the characteristic of dark matter. These are the WIMPs and axions. The weakly interacting massive particles, or WIMPs, would be electrically neutral and 100 to 1,000 times more massive than a proton. On the other hand, axions would have no electric charge and will possibly be very light, with a mass of just 1 trillionth the mass of an electron. Of these two, WIMPs are in particular very popular because they capture the essence of dark matter particle quite nicely. They have mass, which means they have gravitational influence, but otherwise interact very rarely with normal matter. If true, what this means is that the weakly interacting massive particles fly through us on Earth all the time, but because they interact weakly, they just don't hit anything and are therefore not felt, unlike ordinary matter. Over the past few decades, scientists have developed many experimental programs to try to detect the rare interactions between WIMPs and regular atoms. The major problem in these experiments is that on Earth we are constantly surrounded by low, harmless levels of radioactivity coming mainly from trace elements such as uranium and thorium present in the environment and cosmic rays from space. The goal in hunting for dark matter is to build a sensitive detector which can detect dark matter and to put it in a place where the dark matter signal can be observed over the background radioactivity. The Lux Zeppelin, popularly known as LZ collaboration, has done just that. They built the largest dark matter detector to date, operating at 1,478 meters underground in the Sanford Underground Research Facility in Leeds, South Dakota. Their initial results were published in 2023. At the center of LZ rests 10 metric tons of liquid xenon. When dark matter particles pass through the detector, they may collide with xenon atoms, leading to a flash of light and the release of electrons which are supposed to be recorded by the detector. LZ is what scientists call a Generation 2 direct detection experiment. Some of the other facilities belonging to this category are Super CDMS Snow Lab and ADMX Gen 2. In addition, there are experiments focusing on indirect detection of dark matter particles. Some theorists propose that colliding dark matter particles could annihilate each other and produce two or more normal particles. Theoretically speaking, colliding WIMPs could produce positrons. You can think of a positron as a positively charged electron. The Alpha Magnetic Spectrometer, or AMS, on the International Space Station captures cosmic rays. Cosmic rays are nothing but bits of atoms accelerated to high energies by exploding stars. If the AMS detects a high number of positrons in a high energy spectrum where they would not normally be, it could be a sign of dark matter. So far, the AMS has recorded over 25 billion events. It found an excess of positrons within the appropriate range, but there is not enough evidence to state definitively where the positrons originate. There are other possible sources, such as pulsars. To summarize, while dark matter remains a mystery, ongoing research and discoveries offer hope that we may one day unlock its secrets and understand our universe and its contents better. If you found this topic fascinating, check out the other videos on our channel and let us know your thoughts on dark matter in the comments below. I'll see you next week. Until then, take care.